is the last chunk from the section on linear transformations that we did not get to in class. This content is not on the exam. I think that's clearly stated on the website where I posted these. You can use them to finish your homework, but your homework is of course not due before the exam anymore. So for linear transformations, I want to talk about two very important properties, and these are actually properties that are important for all functions in mathematics, and these are central topics to latter math courses. So we're mainly going to talk about them in this class in terms of matrices and linear transformations, but I just want to say up front that these are important properties forever and always. So we're going to work in the framework of linear transformation from Rn to Rm, but we now know and have seen and have discussed at length, if you watched the helpful videos before the exam, that there's no need to make a distinction between the matrix of a linear transformation and the linear transformation, because our big result, which is a theorem and it has a proof and you've seen it now, is that any linear transformation, which is just a function with domain Rn and codomain Rm, that has the property of linearity, and we know what the property of linearity is, any function that has the property of linearity can be represented by a matrix, and the action of this linear transformation is just matrix multiplication against this matrix. Conversely, if I give you a matrix, which in this case would be an M by N matrix, you can always think of it as a mapping from Rn to Rm, again, just by thinking about its action through matrix multiplication. And there's a procedure for taking a linear transformation and producing the matrix, and there's also a procedure for looking at a matrix and determining what its action is as a linear transformation, and that was the subject content of earlier videos. So for these linear transformations, we have been thinking about the equation ax equals y, and of course we've been solving this the entire semester, right? So given a y, we want to find the x's. There are three distinct cases. There is a situation where there is no solution, so that is a particular given y for which there are no x's that solve this. There's a situation where if I give you a y, there is a unique x that solves this, sort of the best case scenario. And then there's a situation where I give you a y and there's actually an infinite number of x's which satisfy this y. So all we're going to do in this short video is just recast those scenarios in terms of properties when we think about a as a function. So the book talks about uniqueness questions and unique solvability. Well, we've been doing this since the beginning. We're just framing those questions now in the context of a function. And so we're thinking about y as being the dependent variable, x as being the independent variable, and a is the transformation that takes you from x to y. So we're going to ask the question, when is this solvable? But we're going to phrase it in terms of the function. And there's going to be two properties which will correspond to these sort of solvability issues. So the property of surjectivity and the property of injectivity. The textbook does not use these terms explicitly. The textbook says onto and one-to-one. Injective and one-to-one are the same thing. Surjective and onto are the same thing. They're just synonyms. I will use both because I've been using both of these words for 20-something years, and it's hard for me to get into the mindset of just using one and not the other, but they are synonymous. So a mapping is onto means the same thing as saying a mapping is surjective. A mapping is one-to-one is the same thing as saying that it's injective. Textbook uses one-to-one and onto. Okay, so let's get back down here to talk about solvability. And so there's two questions I want to ask. And again, you've already asked these questions. I'm going to say that several times, but in terms of solvability. So we're just going to phrase it slightly differently. For which y's is there a solution x? So instead of thinking about a given y and then asking whether there's a solution, we think about the class of all y's, namely all of the y's that come from Rm. We just ask which y's have the property that there is an x that maps onto them. And as you can probably guess, that's where this word comes from. So when we ask about which y's have x's, we're asking which y's have solutions, which right-hand sides have solutions, so that when you apply a to the solution, you get y. Now, the next question is about uniqueness. So if you have a particular y for which there is a solution, again, we know there are two possible cases. Either the solution is unique or there's an infinite number of them. So what we're asking is just a binary question. Given a y for which there's a solution, is there one or are there many? Now, that's going to lead to two different concepts and two different definitions. So in the situation where every y has an x that solves this equation, we say that the mapping A or the mapping T is onto. Okay, so that's what I wrote here. When every y has a solution x so that ax hits y, so every single y in Rm, every single y in Rm, every single y in Rm gets hit by some x in Rn, in that case we say that the mapping is onto. And another way to say this concisely is that the codomain and the range are the same thing. I made a big deal earlier in the course that the range is not necessarily all of the codomain. The range could be a subset of the codomain. So in the special case, when the range is equal to the codomain, we would say that the function or the mapping is onto. Now, when we come down here and we talk about the number of solutions, so when you have an equation like this for which there is a solution, if there's only one solution for every such y, then we say that the mapping is one-to-one or injective, which is just saying that there's no possibility of having two distinct solutions for the same y value. Now, that's not the same thing as saying that every y value has a solution, and it's important that we use mathematically precise language, which I will do on the next slide. But what I want to point out here is when we have a solution, we are asking the question, do we have more than one? If for every y, when there is a solution, there is one and only one such solution, then we say that this mapping has the property of being one-to-one or injective. Okay, so I wrote these out mathematically. Here we go. And I wrote it in terms of the linear transformation just because that's how the book does it. So we say that a linear transformation from Rn to Rm is onto Rm, right, onto its codomain, meaning the range is the same as the codomain, if and only if for every y in Rm, so for every vector which is in the output space, you can find at least one x in Rn, that's the domain, so that y equals t of x. And that is the definition of onto. And I'm just rephrasing what I said before in mathematically precise terminology. Now, injective or one-to-one is often harder for students, but we say that t is injective or one-to-one if, okay, so this says any time that you have two things which are being hit. So you say t of x1, t of x2. So if this equals this, then they had to come from the same place, which is to say you can't have two distinct solutions to this equation. So if you start on the right-hand side, if you were to have two different x's which map to that particular y, that would violate injectivity. So when we want to define injectivity or one-to-oneness, what we're saying is that whenever t of x1 equals t of x2, whenever the images are equal, then the original points where they emanated from have to be equal. This is preventing the possibility of two distinct solutions to the same equation. And again, that's probably the best way to think about it is if for all y's that have a solution, there is one and only solution, one and only one solution, we say that the mapping is injective. Okay, and then I just included here a little argument. This is going to annoy some of you, and the textbook has a proof of this property, but I just put it here. So when we're looking at injectivity, one thing we can do is we can take this if-then statement. So this is an implication arrow. We can move this to the left-hand side. So if t of x1 equals t of x2, I can move t of x2 to the other side. So it's t of x1 minus t of x2. And then because t is linear, I can factor t out. And so what we're seeing here is that this situation for a linear map is actually the same thing if you move it over and you think about this as being some new variable z. This is saying that whenever t of z equals 0, then z has to equal 0. And this is just using linearity. If you don't understand that, that's okay, but the book has a proof that the property of linearity, the property of one-to-oneness or injectivity for linear maps can be rewritten, and I wrote it here. So a mapping is one-to-one or injective if and only if t of x equals 0 has only the trivial solution. This is probably the most useful way for you on your homework to investigate injectivity is if I give you a mapping or a matrix, form the system Tx equals 0, and then determine whether or not there is a non-trivial solution. If the only solution to this has to be 0, and you know how to do that through row reduction, if the only solution to this is the 0 vector, and by the way, the 0 vector will always be a solution. If the only solution to this is the 0 vector, then that means that your mapping is injective. And if you can find any other vector, non-trivial means non-zero, that satisfies this, then that means your mapping is not injective. And that's why I wrote here, you know how to check this. And I just wrote sort of the negations down here for useful homework help. If there are any non-trivial solutions to ax equals 0, then the mapping represented by the matrix A is not one-to-one. And going back to ontoness, if there's any y in the codomain that does not get hit by some x, namely if there is a y so that ax is never equal to y for any x in the domain, then A is not onto. And of course, the way negations work, if it's not one-to-one, then it's one-to-one, and if it's not onto, then it's onto. So that allows you to use these definitions if you prefer them to check for ontoness and one-to-oneness, or you can use the definitions as I presented up here. Okay, so what I want to do now is I'm just going to move this over, and I'm just going to quickly go through what's in the textbook. I've just explained this, but I just want to show you what the book says and how it says it slightly differently. So a mapping T is said to be onto if for each B, so the authors are calling the right-hand side B, for each B is the image of at least one X. And so again, it's just saying if I give you a right-hand side, there's some X which maps onto it. And so they drew this picture of a situation where you have not onto and ontoness. So here you notice that they drew the range explicitly as a subspace or subset of Rm. And so there are clearly vectors which are in this gap which are not being hit. In this situation, you can see it's onto because every vector in the range is being hit by some element of the domain. And they have these cool like little point and stick diagrams. Wait, where was the? I thought there was more point and stick diagrams, but I suppose not. We'll look at this one for one-to-oneness. Okay, so now back to one-to-oneness. So Tx equals B has either a unique solution or none at all. So their definition of one-to-one is said one-to-one if for each B in Rm, the image is at most one X in Rn. Is the image of at most one X in Rn. So the point here is that if you were to look at this mapping represented here fails to be one-to-one because you can see there are a couple of points right in the range that get mapped to by several different points in the domain. Namely, there is a solution to Ax equals B, but there are three of them. Of course, there would be more than them because we know if there's more than one, there's actually infinitely many. But this would be the situation where this mapping is not one-to-one. But if you look here in this situation, so this is a situation where every single element which appears in the range is hit only by one element in the domain. And that's why, coming back up here, equivalently T is one-to-one if for each B and B, the equation Tx equals B has either a single solution or no solution. But there are no right-hand sides, no Y's or no B's that have multiple distinct X's that satisfy this equation. And so then down here, I just want to point out that they give you some examples of which transformations have which properties. So projections, as we talked about in the previous movie, which is a particular type of linear transformations, are not one-to-one. And they are also not onto. And then the transformations so these are reflections, also rotations, are one-to-one and onto. And there are some other discussions down here as well. So then the theorem I wanted to just quickly show you, and again, I sort of presented this proof very quickly, but this theorem says that a linear transformation is one-to-one if and only if T of x equals 0 has only the trivial solution. So if and only if here means logically equivalent. So if you know that this equation is uniquely solvable, then that tells you immediately that the mapping is one-to-one, which is something that we said earlier. So if you're trying to show that a mapping is one-to-one and you're confused about how to do that, you can use this theorem and you can just check this part. So check the solvability of Tx equals 0, and that will allow you through this theorem to determine whether or not it's one-to-one. If this is not uniquely solvable, then the mapping is not one-to-one. If this is uniquely solvable and 0 is the only solution, trivial solution, then the mapping is one-to-one. And then the last theorem just unites all of these things. I'll just say it quickly. If you have a linear transformation and A is given by its A is its standard matrix for the transformation, which you know how to find, then it's just telling you two things. The mapping is onto if and only if the columns of its matrix span. Okay, so some of you had made this conjecture in class. So the linear transformation is onto if and only if the columns span. And T is one-to-one if and only if the columns are linearly independent. So the linear independence and the span properties are being related to the one-to-oneness and onto through this theorem. So this theorem is useful. You can directly check one-to-one and onto-ness using the properties I've just outlined, but this theorem is also useful for a quick check because these are things you know how to do quickly and can often check visually. Right, so if you can tell whether or not the columns span Rm, then you can infer onto-ness without necessarily having to do row reduction or solvability. And if you can see visually that the columns are linearly independent, then you can infer one-to-oneness. Cool. All right, you should be able to finish that section of the homework about these two properties. And if you have questions, you can feel free to email me.